Okay. Okay, for the online audience, I'll start again. So, welcome everyone to this week's Monsoon Cafe. This is week 8. I'm Rajat Masiwal, a PhD student at CEOS, and today I'll be talking about the kinetic energy of Somali jet and its rapid intensification. So, just a quick background. A low-level cross-equatorial flow that turns eastward and becomes zonal at around 10 degrees north is called as the Somali jet. And this jet is a key characteristic of Indian monsoon, which persists throughout the season. So on the right, I have this snapshot that from Null School. I took it yesterday. This is 850 hectopascal winds, and you can see the feature of this cross-equatorial flow that turns eastward around 10 degrees north. This is your typical Somali jet. And this jet is essential for the Indian monsoon rainfall as it transports moisture from the ocean and takes it towards the Indian landmass. Now, this jet exhibits a high kinetic energy and has a sudden increase at the start of the monsoon. So we ask a simple question, what are the dominant balances that maintains this jet? Coming to the next slide. Yeah. So so the Somali jet is seen to have a sudden and rapid increase at the start of the monsoon, which can be seen in these two figures. So first one is from Krishnamurthy and Ramanathan. They plot this 850 hectopascal zonal kinetic energy, and you can see from roughly from 9th June to 16th June, there is a sharp increase in the kinetic energy. Also, the figure at the bottom is by Bose and Emmanuel. Here also you can see they have not plotted the kinetic energy, but some similar metric. They call it jet speed index. And we can see that there is a very sharp increase of this jet speed index. So it goes from its winter mean value to its summer mean value in roughly around 2 weeks, which is much faster compared to this dotted line, which is the first two harmonics being analogous to our annual cycle, which takes somewhere around 2 to 3 months to go from its mean winter to its mean summer value. Thus, this rapid increase of the jet cannot be explained simply as a linear response to sun moving to the northern hemisphere. So the second question we ask is what causes this sudden intensification of the Somali jet? And so the kinetic energy budget helps us answer these two questions. Coming to the equations, we start with the horizontal momentum equation. Here UH is the horizontal velocity vector. We take the scalar product of this equation with horizontal velocity vector again and do some further simplification to arrive at the kinetic energy equation. Here we have the temporal tendency of kinetic energy. So this kinetic energy is the horizontal kinetic energy given by u square plus v square by 2. And the second term in this orange box is the advection of kinetic energy. The third term, the Coriolis term, is small, and we will not talk about it after this. And the fourth term, which is the scalar product of cross-isobaric horizontal winds and geopotential gradient, is the actual source term of kinetic energy. So this just says that only the cross-isobaric flow does work and produce kinetic energy. And the last term is the friction term, which is calculated as the residue of all of this equation. So we will look at each of these terms in the budget in ERA 5 pre-analysis on a daily time scale and 1 degree cross 1 degree horizontal resolution. Before going to the budget terms, let's look at the isobaric and cross-isobaric winds. So these winds are calculated using a simple projection of winds onto the geopotential gradient directions. We can see on the top two panel are the the isobaric zonal wind and cross-isobaric zonal wind. We can see there is a lot of geostrophy prevailing above and below the equator, which is normal. And we also see that there is this spatial region just off the Eastern African coast where you have a lot of cross-isobaric meridional winds. We will see that this region is spatial in coming few slides. But first, let's look at the vertically integrated kinetic energy and the kinetic energy generation. seasonal mean picture. So here the contour shows the kinetic energy, green contour shows the kinetic energy generation integrated from 1000 hectopascal to 700 hectopascal. And the color shading shows the kinetic energy integrated over the same vertical region. So we can see that there are these four dominant regions marked by these blue boxes, which have high kinetic energy, namely the southern hemispheric region, the just north to equator region, the northern hemisphere region, and the Bay of Bengal region. We also see that there is high kinetic energy generation, especially just off the coast of East Africa, which is the same location where we had a high cross-isobaric meridional winds. We also see a lot of kinetic energy generation at the locations where there is a presence of orography. So this points towards the orographic lifting and the kinetic energy generation of because of that process. Now, looking at the each of the term in the seasonal mean budget, so we can see that. So on the top, I have all the temporal term and the advection term. And the first panel at the bottom is the material derivative. We can see here near the Eastern African coast or the just north of equator, there is an acceleration of the jet, which is caused by high source term, the generation term, coming mostly from the meridional component of the generation term, and surprisingly a very small frictional term. And when we go further poleward, so somewhere above 10 degrees north, where the jet turns zonal, there's a lot of friction and the generation is small. Thus, there is a deceleration of the jet. So now quantifying these balances by taking averages over the four boxes that we had identified earlier, we can see that in the southern hemisphere box and the Bay of Bengal box, the balance is mostly between the frictional dissipation and the generation coming from the meridional term. And this is a Ekman type boundary layer where friction balances the geopotential or the pressure gradients. Then coming to the northern hemisphere, we find a three-way balance where the friction dominates and the advection as well as the generation tries to balance it. And the spatial region in just north of equator is where you have this non-linear balance where the meridional generation of kinetic energy is balanced mostly by the meridional advection of kinetic energy. So here we have this advective boundary layer, which is non-linear in nature. And this kind of balance can be actually characterized by this local Rossby number, which is a non-dimensional number, giving us a ratio of advective acceleration to the Coriolis acceleration. So we can see here in the x-axis of this plot, the Rossby numbers are plotted. We can see for a very small Rossby number regime, we find a Ekman type balance, whereas for a regime where the Rossby number is greater than 1, advection of course dominates, and you have a balance where the boundary layer is advected. This is also confirmed through the latitudinal structure of these balance terms. So here we can see for region where R0 or the local Rossby number is very small, the balance is mostly between this green curve, which is the meridional generation, and the red curve, which is the meridional, the frictional term. Coming just next to the equator in the northern hemisphere, we see that R0 is greater than 1. So the advection term dominates, and this advection term balances the kinetic energy generation, this green curve, and the frictional term is small. But going further poleward, this frictional term starts becoming important as the jet becomes zonal. And then we have a three-way balance between friction, advection, and the generation term. Now, so we see that R0 is a good quantity to characterize this balance. So we look at the seasonal dynamics of boundary layer Rossby number, local Rossby number. Okay, I want to emphasize that this R0 is calculated at the same level where the balance is. So in the boundary layer, 900 hectopascal. I will talk about the upper Rossby number later in the slides, but here we can see that for the winter season, the R naught equal to 1 contour given by this green line sticks close to the equator, whereas when we are in the monsoon region, monsoon time period, we can see that this R naught equal to 1 contour moves poleward in the northern hemisphere, and from equator till this contour, we will have R naught being greater than 1 and the boundary layer being advective at this region. This was all about the seasonal dynamics of the jet. Now we will talk about the rapid intensification of the jet. And so we focus only on this region where we have advection prevailing, namely the north of equator region. And here we see the evolution of kinetic energy and the kinetic energy generation for one representative year, 2019. But the picture remains more or less same for any other year. We can see this blue curve showing the kinetic energy rapidly increases from this almost at the end of May to mid-June. And this rapid increase is also seen in the kinetic energy generation. Further, we see that this kinetic energy and kinetic energy generation are highly correlated, and this correlation increases during the monsoon period, which is shown by this scatter plot of different months for all these 42 years from 1979 to 2020. So, but we had already seen that this kinetic energy generation mostly comes from its meridional component, given by this expression, the VA times d phi dy, VA being the cross-isobaric meridional winds and d phi dy being the meridional geopotential gradient. So we now look at the relationship between these two terms. Figure on the top here shows a scatter between d phi dy, the meridional geopotential gradient, and VA, which is the cross-isobaric meridional wind. And we can see that there is a nice strong relationship between these two terms. Now, this relationship translates into the kinetic energy generation having a quadratic nature, which is seen in the second plot, the plot on the bottom, where you can see how nicely. So this blue dots are your kinetic energy generation scatter with d phi dy for all the 42 years, and this parabolic curve is the best least square fit of this data. So, and so this form of when you do a least square fit, you'll get an expression like this. So this tells us that the kinetic energy generation has a quadratic relationship with the geopotential gradient, and this leads to the nonlinear increase of your kinetic energy generation, and then further kinetic energy, which is correlated with kinetic energy generation. This can be seen in this plot. Here I have plotted the net solar insolation in blue, and you can see how slowly this insolation evolves on a monthly time scale, well, more than a month. And we have this geopotential gradient, which is rapid, but not as rapid as the kinetic energy generation given by the green curve. Also plotted is the red dotted line, which shows the kinetic energy generation coming from this model. So this quadratic model that we obtained from the least square fit. And we can see this quadratic model actually performs very well for 2019, and it does for any other year as well. And for this model only needs a geopotential gradient, and it will give you a kinetic energy generation. And here we can see that the generation has twice the growth of kinetic energy generation is twice as rapid as the geopotential gradient. Point to note here is that all these variables are scaled from 0 to 1, doing a mean max scalar. But yeah, so this is just a way of representing the rapidity of the kinetic energy generation. And also looking at the balances 15 days prior and 15 days after the onset. So here the onset day is selected as using the criteria by Wang et al. 2009. And this study uses the 850 hectopascal zonal winds as a metric for quantifying the onset of monsoon. So we use that criteria, and we see that 15 days prior, 15 days before the onset, the local Rossby number is 0.43, less than 1. and this frictional term dominates. And the frictional term mostly balances the generation coming from the meridional term. But 15 days after the onset, the Rossby number exceeds 1, and then you start seeing this advective, nonlinear advective balance between the meridional generation VA dphi dy and the meridional advection of kinetic energy given by V times d ke dy. If we do a composite evolution of local Rossby number at 900 hectopascal, we can clearly see that a month prior to the onset, this local Rossby number is close to 0, and after the onset, this variable settles at a value which is greater than 1. So is this a signature of regime change? Well, we don't know for sure, but we can. I want to bring into attention this study by Bodoni and Schneider, which looked at the local Rossby number in the upper troposphere and related the Hadley cell transition with this variable, the upper level local Rossby number. So they found that when before the onset, you have this local Rossby number being less than 1, so okay, close to 0, and then you will have these two Hadley cells in the southern and the northern hemisphere. And once the onset is reached, the local Rossby number in the upper troposphere comes close to 1, and you have the single Hadley cell where the angular momentum is conserved in the upper troposphere. But the study does not talk about the Rossby number in the lower troposphere, which interestingly we find has even more clearer rapid increase going from 0 to 1 before and after the onset. So to summarize, we see that the boundary layer up until 10 degrees north during the monsoon is advective, and the local Rossby number exceeds 1 in the northern Arabian Sea. We also see that immediately after the onset, the balance of Ke shifts from one being dominated by nonlinear advection to one being dominated by kinetic energy generation. Also, the rapid intensification is seen in the kinetic energy generation term, which is caused by the nonlinear response to the meridional geopotential gradient. So this was all I had about the Somali jet part. And so I just have 2 or 3 more slides where I wanted to discuss this Granger causality, because we had this discussion last week as well. And I found this paper, which I think is very nice. And I want to discuss a couple of results from this paper. First, looking at the definition of Granger causality. So a time series X is said to Granger cause Y, different time series, if the past values of X provide information about current state of Y beyond what is already available from the past values of Y alone. We will see what that means. But in order to determine the causality, we make 2 prediction models. So the first one is the restricted model, where we use Y to predict Y. And this is given in this bottom here. So Y at time t is predicted using the previous time histories of Y. And then we have this unrestricted model where we use both X and Y to predict Y. So here time histories of Y prior to t and time histories of X prior to t are used to predict Y at time t. This is the unrestricted model. And if the unrestricted model performs better in terms of predicting Y as compared to the restricted model, we say that X Granger causes Y. That's the theory. I'll skip most of the details. I'll just show these 2 results from the paper. So here they make a synthetic signal D of t. D here stands for the driver signal, which is sort of like a red noise signal, where this alpha is the first lag autocorrelation, and D depends upon time history of t prior to the time t, and this epsilon D is some Gaussian normal Gaussian white noise. So this is the driver signal, and then we have this R of t, which is a response signal, which depends upon the driver signal. Now, what they did was they tried to use the Granger causality test to see if So they have two cases, going from the actual case where you go from D to R. So in the positive direction, the correct direction, and then going from R to D in the incorrect direction, because we already know from the formulation that the response function does not cause the driver function. Here they find that in the first case, when you are going in the right direction, you actually do see that this Granger causality passes, and for most of the values of alpha and gamma is the noise in the response function. Most of the values of gamma and alpha, you have the Granger test passing and showing that yes, D does indeed cause R. And going in the reverse direction, this test have some false positives, but more or less it shows that R does not cause D. And this final slide, where so they did this same technique for the the surface temperature in the American continents and the ENSO signal. So here they show a very nice difference between the lag regression and the Granger causality, these two techniques. If you do a lag regression going from ENSO to TS, meaning that ENSO causes the surface temperatures, which is the reality, you see that the lag regression passes for all these grid points. But if you do it the other way around, meaning that the surface temperature in the American continent causes ENSO, you still see all these grid points passing the test, which is not the case. But if you do it using the Granger causality test, you can see this nice difference where when you are going in the right direction, all these grid points, most of these grid points pass the test, but going in a reverse direction or the incorrect direction, you don't see a lot of grid points passing this test. So I mean, Granger causality does have is a nice tool to see if there is a cause and effect between two variables. But there are a lot of caveats associated with this test. And if someone is interested, they can go through this paper and see for themselves. But yeah, these are the references I have used in my talk. Thank you. Yeah, that's all I have. Any question? Friction with generation, kinetic energy generation. No, this just means that when the local Rossby number is very small, the advective terms are small, and then in the momentum balance, you will have the frictional term balancing the gradient term, the geopotential gradient term. Yeah, so okay, so I mean the Coriolis term will be there, but you are near the equator, so the geostrophy will anyway will spawn, right? No, we have just quantified these using the local Rossby number. We have not looked at the Ekman number. No, this is reanalysis data, error 5, yeah. No. This friction is calculated as a residue of all the other terms. Yeah, it is not a pure friction. Yeah, but we did some calculation using higher resolution. So this results are shown at 1 degree cross 1 degree. We have done a calculation using 0.25 degree data as well, and hourly data. Result does not change much. So these subgrid scale processes probably do not have a lot of effect when we are calculating residue as just the friction. That's my guess. Yeah.
So I have many questions to you, but
Sure.
one question is that what happened to the, say, we have shown that in BJS and me, in our paper, we have shown that even without the orography, in aquaplanet model,
Yeah,
let's say, we have Somali jet is present.
Yeah.
Right? But from your plot, it looks like that most of your generation is along the orography where there is a friction in the, like a change in the topography.
Yeah,
Right? You
yeah.
also mentioned that.
Yeah.
How do you explain that? How do you explain?
Yeah, so I guess the orographic generation, generation will come wherever you get some ageostrophy or some cross-isobaric flow. So most of the places where you have orography, cross-isobaric flow comes because of friction. You have friction, the winds have to cross the isobars. But this location is special because you have an advective balance. So the Coriolis term cannot overall balance the gradient, the pressure gradient term, and for that reason, ageostrophy has to come in to balance the remaining the nonlinear term from the advection, and that is where this generation comes, and probably even when you remove orography, this generation will still be there.
Yeah, so that's the reason I'm saying. So that comes to the next question. That seems that basically you are saying that there is something else,
Yeah,
which plays a role, right?
Yeah,
because,
yeah.
Because in your generation term, your VA dot or VA times your
Divide,
alpha
divide.
del y.
Yeah,
So if either one is zero, you won't get generation,
Yeah, yeah.
isn't it?
yeah,
So, but both of them are related to something else, right? So there is
yeah.
something else which is driving,
Driving, yeah, yeah,
isn't it?
yeah, yeah. I agree. I agree.
Any question from the online?
Oh, yeah. I think this is recent study by Shishadri and Dikshit, where they show that the convective precipitation does not really play much role, at least in the Somali jet, in the lower tropospheric kinetic energy. Yeah. Mm-hmm. Could be that for this onset to occur. Mm-hmm. Yeah, yeah. But I guess in this probably it affects d phi dy. So the gradient of geopotential is affected by yeah, d phi dy. Yeah. So the convective heating. Hmm. Yeah, yeah, yeah. We have not looked at the dynamics of d phi dy as of yet, so I cannot really comment on that. No, I don't think there are any questions.
Actually, the comment you made about Granger Causality is very good. I have followed to read that paper because very common mistake made in this field. Here in our region, international variation of rainfall can have existing. Okay, if you do a lead lag correlation, you can put anything you want. So there is a 15-day oscillation of both. Okay? And to show A causes B or B causes A, you require that stress lagging function, which is not normally done by most people in our field. So I think we made a very important paper. I think if some of you find it difficult, maybe you should give a separate talk on that paper as to how two time series, which are similar kinds of time scale, when they interact, how to prove which is causing which. Although I find it very interesting, I still have a doubt because many of these statistical methods, there are assumptions made to write the answer. Now, I would like to know what assumptions they have made.
So first assumption is that they use a linear model to predict, right?
Okay.
So when you predict y with time histories of x and y, you use a linear model, but that model is of your choice. You can also parameterize it in a way where you can use instead of x, you can use x squares as well. So so there are a lot of modifications that you can do, but then the implementation becomes harder and harder as you.
Yeah, I remember paper published what I don't know, very long ago. Big argument with somebody from IIT on this SST called the rainfall college history. You remember that? Huh? No, I think because both rainfall SST have a similar time variations, one can conclude that SST causes rainfall. But actually rainfall also includes SST. So the two get buried up if you do, let's say, these like regression over about 1 month. We don't know whether the last oscillation caused this rainfall or very tricky problem. So this may have some light on it. Yeah. So I think you made a good point. I thought Granger Causality was no different from these like little bit more. But it demands a model. That's what worries me.
Yeah.
So if you don't have a model, what do you do?
Mm.
That issue, maybe somebody would have looked at that. I think it's a very good paper and what you can take.
Yeah. No, let me share the slide again. Yeah, but when you use the data, okay. Yeah, when you use the data, so these red dots just represent that your test passes here. But the test is done in a way where you will take this kind of a model, a restricted model and an unrestricted model for each grid point. And for each grid point value, you will have a value for time, the surface temperature and an ENSO time series. And then you use this a linear model to, yeah, fit this B1, B2, B3, and so forth, depending upon the number of lags you take.
I was thinking that in our case, look at NO 3.2 SST. In my view, if the autocorrelation is less than the cross correlation with rainfall, we can believe that. But very simple thinking when I look at it regressively, that cross correlation, how much high it should be compared to autocorrelate for it to be.
So
right?
they make this point that actually this reverse order, so TS causing ENSO is because ENSO has such a high autocorrelation.
Right.
You in the reverse order also you see this lag regression being giving false positives.
Okay.
So that's why Granger causality is better. They say that it takes care of. It takes so it will first remove the predictability of ENSO coming from ENSO, and then it will feed in the predictability of ENSO coming from TS or Monsoon for our example.
But they are not done rainfall in this paper.
No, they have only done. I guess this was an easier result to show. That's why they did this one. They have not done rainfall.
Yeah, that's very interesting.
Yeah.
Okay. Thank you.
share. Share screen. Okay. I think you want me to go and
Okay, good, yeah.
okay.
Yeah, so as of today, I don't have today's data, it's still not been uploaded by IMD. As of today, I think the cumulative rainfall from June 1st to July 20th will be around 380 millimeters, okay? It's pretty high. Why is that? Because we have 11 more days to go for July, okay? And if everything goes normally, we'll get 100 more millimeters. So we are looking at June, July rainfall anywhere between 480 and 500. If that is true, then we are going to a JJ's rainfall around 900 millimeters or more. Okay, that's very interesting. And second thing I want you to notice is that during July, the departure of orange rainfall from normal is 33%, which is very high. Okay, and if you look at central India, it is almost 89%. So this is very unusual, and this happened because this system was sitting over Nagpur essentially for almost a week. It didn't move north. Okay, and so Uttar Pradesh and Bihar suffered heavily. And if you look at homogeneous, also you can see clearly northwest and northeast India suffered badly. They had below normal rainfall, and both central India and South India both did very well. And although I don't have the 20th July actual data, I don't know why, they have put up the actual rainfall till 8:30 this morning. You can see clearly, yesterday was not a great rainfall day. It rained only in certain regions of northwest and Jammu and Kashmir and maybe Punjab. Most of India was dry. So if you look at all India, I don't have the number. I think it's around 5 to 7 millimeters up to 20th morning. Okay. If my prediction that by July end we'll have cumulative rainfall of the order of 500, then in this graph where I show the possibilities of various values, you can see that we will, if you look at the red one above, red one is June, July between 450 and 500, and the yellow one is 500, 550. Suppose we cross into 500. Now, according to this climatological data, there is very little chance that we'll get between 8 and 100, only 2 cases out of 18 cases. So most probably will be in the region 900 to 1000 millimeter range. That's what looks like. Okay. Now, if you look at the last week's rainfall, on the left is the observation from IMD 7 to 13 July. On the right is forecast, but 8 to 14. Always there is a 1 day displacement, unfortunately. But what you want to notice is that they cut correctly the rainfall over central India and northwest and also south, but they get wrong the Uttar Pradesh, Bihar lack of rain. They don't get it. They show some rain which really is not there. Okay. So so this is the in the forecast. This was the problem. They predicted some rain in this region, but actually didn't rain. But they were off by a few days. Today is raining like anything in Uttar Pradesh today. Okay. Right now, I'll show you the windy figure. Yeah, I must also tell you a very interesting thing. I forgot to note on the paper. Many people have done EOF analysis of Indian rainfall. Okay, so it has 2 modes. The first mode is what all of us know about, is the dipole between northeast and rest of India. Okay, that's very well known. That explains only 31%. Surprisingly, I thought it explained more than 31%. The second one is what was happening last week. North-south, okay? Uttar Pradesh, Bihar, West Bengal had no rainfall, and Central India and South India had more rainfall. This is only 11% variance explained. So we went through that phase for 1 week. Now I think it's gone now. And now we see what happened at 2:45 p.m. today. Okay, from windy you see is a huge blob sitting over Uttar Pradesh and Bihar. And we hope it brings enough rain because that area has been having no rain at all for the past 1.5 months. Okay, so this is good news for the heart of the Indo-Gangetic plain. How about the forecast? I would say that all India forecast is never right actual number. Okay, but the trends are all correct. For example, it showed increase from 9th July to about 13, 14, then started decreasing. The only difference was the forecast said decrease occurred on 15, but it occurred on 16. That's not bad, 1 day delay. Then slight increase is showing here, and that will again start declining from today. So today's is not today's prediction for 20th was around 14.5, but the real number will be somewhere here. Okay, we'll know. I'll tell you next week what the number was. Now, if you look at the weekly average prediction for the week of 15 to 21st, which includes tomorrow also, it's almost close to normal, minus 0.8%. And if you look at all the numbers, it's very close to the right number. So this prediction was correct. And the next week's prediction is plus 8%. We will see whether it comes true or not. Now let's look at the MJO status from Mike Winter's website. You can see that the MJO is somewhere here. The main part is not very strong. It's very weak. So the effect over India is almost nothing, neutral. For India, neither there is upper level divergence or convergence. And it goes all the way to August 8th or 9th. Is it August? August 3rd, okay. So till the end of July, we have no possibility impact of MJO. So I expect that all India rainfall continue to be normal till the end of July. So that's why I'm predicting it will be close to 480, 490. We'll see what comes through. Now, what's the forecast from GFS? The forecast is that it will continue to rain in Uttar Pradesh and Bihar in the next 1 week, right there. It will somewhat weaken near the end of July, and August will be somewhat normal. So there's a possibility there will be a break somewhere in August, maybe. But it's also interesting that over the Arabian Sea, there's a huge negative anomaly. We'll see whether that comes through or not. This is the comparison between GFS forecast and ESMW forecast. I'm showing it to show that by and large they are same. This is not anomaly, the actual value. And you can see by and large, both of them say in the next, in the current week, coming to July, the rainfall will hit the Uttar Pradesh and the foothills, and it's happening already. Okay, so slight difference, but not too much. So we can believe that this is what's going to happen this week. Next one is a week of, 2 weeks. And this is anomaly. Anomaly is better because each ball has a different mean rainfall. So again, I would say that except for this portion, this region that is showing a strong negative anomaly that is below 100%. Otherwise, ESMWF and GFS are very similar. ESMWF is showing a slight negative anomaly, which is not that strong in GFS. Otherwise, this pattern is very similar for the entire 14 days till the end of July. So based on that, I believe that we'll have a normal all India rainfall. Now, I want to show you the very interesting this part of this prediction. The prediction which says good India had what will be the rainfall. This is from 4th to 17th July. This is past, not the future. Okay. What I want to point out is that this descent over Uttar Pradesh and no rainfall is linked to what's happening in China. Okay, so that's very remarkable. This is not a local phenomenon. This goes over Tibet, over East China. So there's some large-scale phenomena which is affecting Uttar Pradesh, Bihar, and West Bengal. Very interesting. And of course, something is also happening in this region, Southeast Asia. But I think this linkage is what I think is interesting. And this is the prediction till 3rd August. Very similar, both of them. So I would say that that's why the feeling is that it will be a normal rainfall till the end of July.
Sorry, I didn't put the numbers there. Okay, I want to say a few words about the ENSO monsoon connection. We had discussion and we said monsoon must affect ENSO. So I discovered that I should have known this paper. Kitman and Shukla published paper 22 years ago in the Quarterly Journal, in which they ran a model to demonstrate the role of monsoon on ENSO. Okay, so I strongly recommend all of you read it. And what they're saying that based on the coupled simulation, a variable monsoon enhances ENSO variability 3 to 6 months after the monsoon ends. This is from model output, okay, and can also serve as a trigger for the next ENSO. So ongoing warm event is made warmer by a weak monsoon. So they are able to show that if monsoon fails over India, the developing El Nino becomes stronger. Okay. And similarly, if there's a warm event in the Pacific and Indian monsoon is above normal, it will weaken that. Although this was not true in 1997, but that may be an exceptional case. So this is an interesting paper, but I would like to know how good the model reproduces the climatology of ENSO and monsoon, because this is a 22-year-old model. So one has to look at it, but it's a paper worth reading because the authors really had already seen what I had said should be done. Okay. Now, there's a recent paper published a month back by Pascal Terre, who comes very often to this center, using Syntax, the French model, coupled model. And what's interesting about this paper is it's mainly on Atlantic Ocean, but what I found nice about this particular graph is that the lead lag correlation, this is the observation, the blue line, which we discussed already, that the correlation is large 1 year before, it rapidly goes to 0 just before the monsoon. Then during the monsoon, it picks up because very negative, and then it goes back to 0. This is observation. Look at the model. The model, none of the version of the model captures that. So to me, that is bad news. And so this is surprising. This is 22 years after Shukla's paper. So I'd like to know what happened. Why are models getting worse? I don't know. It's worth examining. Maybe it's just this model. So it's worth examining whether how many models correctly reproduce this cycle. To me, that's a prerequisite. If it does not get it right, I won't trust this model to tell me about ENSO monsoon connection. So they don't get the right lead lag correlation. Okay. So this is what looking at in more detail. Now I want to end by talking about what happened yesterday in England. England had the hottest day in the last 300 years. So England is a country which maintains very good data. Okay. And you must remember they are the ones who established the rain gauge network in India. So they have very good data collection. They have data going back to 300 years. And this is the highest temperature ever recorded, 40.2 degrees centigrade. Okay. 19 July 2022. And notice that all the high temperature records in the last 100 years occurred in the last 40 years. Only one example in 1910. Okay. This is a clear evidence of the impact of global warming. Okay. So this is not only that, what's interesting is the weather forecast models are so good today that almost all the models predicted 40 degrees centigrade 5 days before this event. So they were very good. That's because remember, predicting heat waves is not a difficult problem. It is not rainfall. You have to make sure that your winds are right. You have to make sure that you're getting the right area of descent, because descent causes heating. And you must have the correct rainfall in the days before the heat wave. All the three are required, and all the three they got it right. So to me, this is a good indication that almost all weather forecast model can predict a heat wave at least 3 to 4 days in advance, which is good for purpose of adaptation. Now, what's interesting is the UK Met Office, which is the leader in many of this work, they wrote a paper last year saying that by 2050, in the month of July, this kind of event will occur. Okay, they said that last year. This year it actually happened. I mean, this is mind-boggling. I can't believe it. So seen on a headline that what was predicted to occur 30 years from now has happened already. Okay, so this exact pattern, which was predicted by UK Met Office, actually happened. This is of course hypothetical. This man is not real, imaginary man. This is a real forecast we made a day before. You can see it's very, very close to numbers, except one number is 43, which is not there. But to me, this shows that weather forecast models which are predicting heat waves increase. For example, many models have said that heat waves in India and Pakistan have increased 100 times due to CO2 increase, 100 times. Okay, so this is a warning for all of us. It's going to be a tough situation. The only good news is that weather forecast is improving. So these heat waves will be forecast 3 to 4 in advance, and the society and the government can take actions to handle this heat wave problem. Okay. Huh? Huh? Yeah, that's the other why. Yeah, this is different. So you have to understand this. Okay, I'm showing that this year this heat wave is partly caused by very warm in Africa. As Africa is coming here, yeah, that is a different situation. You're right. Yeah, another possibility. This is they have done a composite. I don't know. I have to check what they have done. I couldn't get the paper. There's a paper somewhere. I have to get the paper. It may be a composite of many events. Could be. But you're right. This is colder than normal. This is warmer than normal. I'll show you that what happened yesterday. Yeah, the first thing you see what happened yesterday is because few days before 19 July, the rainfall previous 2 weeks, rainfall was well below normal in Europe and in England. That's a first requirement for a heat wave. Okay, remember that. Although we can all say climate change is called the heat waves, no, they don't cause heat waves. Heat waves occur due to a confluence of a number of factors, and global warming merely enhances it. It is not the cause. So let's not believe it's not the cause. It is one which modulates what's already happening. So for heat wave to happen, first thing is you must have below normal rainfall 14 days before that event. That happened this year. You can see rainfall was half or 1/4 of what it should be in the month of July. Okay. Next, the wind has to come from Africa. So on 17th of July, 2 days before, winds moved from Africa to England. Advection. And as Arena pointed out, Africa had above normal temperature already. The above normal temperature, tropics are anyway warm. They bring in hot air to a cold area. That's why remember that the heat waves in Europe and in Russia are typically 10 to 15 degrees above normal. Now that will never happen in India, fortunately, because we have this barrier in the north, which will, our barrier only prevents cold air, but we are already in the tropics where gradients of temperature are small. But in European region, advection plays an important role because of the large temperature gradient between Africa and Europe. So anytime the wind comes from Africa, you're in trouble. Okay? So that's the second part. If this had been moving from north, there will be no heat. Okay. And the third requirement is sinking motion. So on 17th July, the sinking motion was over Europe, but it's mainly Spain, Portugal, and France, and they had forest fires and deadly heat waves. Then the next 2 days it moved here. I couldn't get the data for yesterday. It moved over here. I'll show you next week. This thing moved over here on the 19th of July. That's why the heat wave there only 1 day. It's not a long heat wave. Okay. India is different. India, these are all part of the Rossby wave system. You can see that. So these keep moving. For example, right now the heat waves over Germany and move over to Russia and so on. Indian heat waves are different. They will be much longer because they'll be almost stationary. Yeah, I think I'll stop there. This is this is not the part. Yeah, I think I'll stop here. Any questions? I think there's further things. I think nothing much is there. I think I'll stop here. So any question? Anybody have a question? Can we check about online? Anyone? Nobody? Okay. Thank you. So next week it will be Mayur, right?